Okay, welcome everybody to the July technical presentation brought to you by the IEEE MTTS Santa Clara Valley San Francisco Joint Chapter, also known as IEEE MTT-SCV. My name is Utkarsh Krishna. I'm the chairman of this chapter, and the topic, the title of today's talk would be Toward Democratizing RFIC Design, and the speaker, of course, is our own chapter vice chair, Mr. Tom McKay. It's a very relevant topic, relevant in so many different ways, and I'm glad that Tom agreed to do the talk. So thank you, Tom. Before we go on to the talk itself, let's take a look at the agenda for today. So we'll look at the meeting notes, quick COVID-19 update, then we'll look at the chapter officers for both MTT and GaAs-SCV. And then we'll go into the details of the talk itself. Q&A will be throughout the talk at like 15-20-minute intervals, after which we'll take a quick look at next month's talk before closing the proceedings. So a few things to note, this meeting is being recorded and it's being broadcast live on Zoom. Links to the recorded video and slides will be sent to all registrants. So if you registered, you'll get an email from us in a couple of days with those links. Please keep your cameras off and microphones muted to help with bandwidth issues and background noise. Please ask your questions by using the raise hand reaction button towards the bottom of the screen. We'll take breaks every 15-20 minutes or so. We'll unmute you in the order in which you raise your hands and you can ask your questions. Please also ensure that your display name in Zoom matches the one you used to register. This will make it easy for us to check you in. Okay. So same as before, all in-person meetings related to our chapter remain canceled. Our monthly technical meetings and the officer meetings will continue as before in an online webinar format until further notice. So please join the IEEE and the MTTS. The members of the IEEE inspire a global community through highly cited publications, conferences, technology standards, and professional and education activities. The Microwave Theory and Technics Society focuses on the theory and applications of RF guided wave and wireless technologies. So we need your support to keep bringing you these talks from around the world. So please do support us by becoming a member. Take a look at those two links we have there. The details of all the benefits of membership are detailed there. And of course, if you're on LinkedIn, please subscribe to the hashtag MTT-SCV so that you are informed immediately whenever we make a post about upcoming events. So to walk us through the chapter officer lists for both chapters, I would like to call upon our treasurer, Mr. Than Tu. Than, take it away.
Thank you. Of course, I have the pleasure of introducing the officer for the chapters. The chair is Mr. Utkarsh Krishna. The vice chair is Mr. Tom McKay, who is also going to be our speaker today. Secretary is Mr. Venkata Gadi, and will be joining us shortly. I'm the treasurer. My name is Than Tu. Next page, please. We are also hosting in conjunction with the Silicon Valley Circuits and Systems Society. And the officer for that chapter is listed here. The chair is Amit Char. The vice chair is Mr. George Chen. Treasurer is Haimin Chen. And secretary is Si Chen. With that, as we've introduced before, Mr. Tom McKay will be presenting the talk. And the title of the talk is Towards Democratizing RFIC Design. I'll turn over to Mr. Tom McKay.
Thank you, Tim.
All right. Hello, everybody. Can you hear me okay?
Yep, I hear you.
So I want to talk today about democratizing RFIC design. You know, the IEEE, as was mentioned, is about advancing technology for humanity. And the Microwave Theory and Technique Society, we really look at megahertz to terahertz. So the whole range. The frequency range we're talking about here is probably more in the Wi-Fi frequency ranges, and up through 6-7 gigahertz. That's the immediate opportunity that I'll make clear, I suppose, by talking about the particular process that the actually it was the Solid State Circuit Society in April of this year presented a webinar called Democratizing IC Design. And I've actually become aware of the open source kind of activity being done by Google and Skywater starting about a year ago. And so this talk is intended to talk about things that are important when you're working with a process and you need to do something with it at an RF level. Things are going gangbusters at the digital level on this sort of thing, but RF requires some special care, and also we need to collaborate. So one thing I want to make clear is that this is my disclaimer slide. I'm affiliated with Global Foundries. Global Foundries is my employer. It's an awesome company. I love working there, but it's not who I'm representing today. I represent myself, and my affiliation with the Microwave Theory and Technique Society. I've been a member since 1984, 85. And so, this is going to be the property of the IEEE, and it's going to be made public. So democratize means make something accessible to everyone. Okay, so that's really cool because it may have been noted in the earlier slide there that I think I'm really interested in widening the accessibility of our vocation in the Microwave Theory and Technique Society, and this is a great opportunity to do that, following in the wake of the Solid State Circuit Society efforts in this area. Innovation, there's a pattern to it. I've been a student of the Christensen theory of innovation, and I find it valuable as a guidepost and a way to think about what's happening. So I want to talk about this for a few minutes and mention that disruptive innovation, which was, it's a technical term actually that Clayton Christensen identified during his PhD research. And it describes a process by which a product or service initially takes root in simple applications at the bottom of the market. And it's less expensive and more accessible, to more folks. And then it moves up market. Now, the disruption, it happens when established players are displaced. Here we're innovating on low-cost RFIC design, the mainstream simulation technology and other things that have been developed in the last 20 years to do effective RFIC design in the mainstream and in the high end are incredible. Okay, I've seen the industry go from PC S parameter touchstone style analysis to you know, to 22 nanometer CMOS RFIC design using very advanced simulation techniques from the mainstream EDA vendors. So that's a very high-end market and very capable. The disruptive piece comes in when, or the innovation comes in when you know, you have a distribution of the market, of what people can use. And the reason why the incumbents tend to be servicing the high end of the market is because you know, it's the most profitable. So the low end is least profitable, and there's very little motivation to go to the low end by incumbents, large incumbents, say, because there's just very little profit there. It's like, why go there? The challenge comes in, and we've seen this in several areas. You know, IBM years ago was offering, you know, its own version of Unix and other things, and it was used by many folks. And they just bought Red Hat, which is kind of a low-cost, open-source, Linux-based, you know, software company. So these things are coming full circle, and you could say that that low-end trajectory, you know, eventually displaced certain operating system efforts, and that's where sort of the disruption comes from. Disruption doesn't mean it ruins your day. Disruption is a real sort of technical term. I just want to point that out, and I think this can be a real guidepost for what we're doing. You know, to that end, I'll show you this next slide, which is what's going on with open MPW shuttles, which are Google sponsored, actually. And there was one in February where chips are going to be delivered in September, and another one in June with chips delivered in December. And you can go to the eFabless website and see this. And eFabless figures prominently also in the Solid State Circuit Society presentation from April. So, okay, the big thing here is you get access to this process with not having to, you know, it's publicly available. You don't have to sign NDAs and all that sort of thing. And it's an interesting 130 nanometer CMOS process. It supports 5-volt IOs, 5 levels of metal. The advertisement here is that it's inductor capable, has MIM capacitors. Interestingly, it includes flash. So that's what Sonos is all about. And you can get all the details at this link. One of the details is shown here. So, you know, it's relatively thick top metal. And, you know, basically it's all open for you to see. When you dig into the PDK details, you can see there's RF FETs, and you know, there's a GDS layout. There's a BSIM4 SPICE model associated with it, and you know, there's various gate lengths, and it's pretty. I assume it's pretty comprehensive. And you can see IV data, but we don't see any S parameter data, and we, as far as I've seen so far, we're not seeing any RF noise data. I may be wrong, and maybe just haven't dug in close enough, but definitely chatting with folks, I think, you know, there's a need for some of this RF information. I haven't dug into it, but reliability data is really important as well. You know, in RF circuit design, we're routinely not using a digital waveform, you know, of course. And for example, in a VCO, you know, it's common to push it on the voltage to try to get the largest signal on the tank, and you know, minimize your phase noise by maximizing your power in the signal. in the oscillator, and that pushes reliability. Traditionally, how that's handled is the designer realizes he's coloring outside the lines of the digital, manual, and sends his waveforms into the foundry, and those are reviewed and then sent back. No, this won't work, or yes, this will work for 10 years, etc. That obviously is not going to fly here, but I want to caution folks who may be unfamiliar with RF that it's this, you can easily get well above VDD when you apply the kind of biasing circuits that we use in RF. So a choke, for example, just sets the average value on the other side of it. So you can have an average value of 1.8 volts, but easily get to twice that value on the transistor side of the choke, and even 3 or 4 times that, depending on the waveform. So this is kind of restating what I think we need, and I'm going to try to go into some of these things here. So let's sort of take a look here. What I think we'll talk about here is receiver design. I think it's a good starting point. Really good LNAs are hard to do. You have to be meticulous, so what is a receiver design basic requirement to do something useful? I'm going to sort of identify a minimum requirement, and then it's really important to get model hardware correlation, and that's with regard to active and passive device models to start with, which you then can design with some determinism with those. And so we need on wafer, and when you build your part into a test circuit, test board, you need PCB S parameter measurement. We also really need, and I'll talk about a little bit, is RF specific circuit simulation. And there's 2 pieces to that. As a minimum, linear scattering parameter and harmonic balance. Now, SPICE simulators typically are limited to transient and classic AC analysis. And folks did design RF circuits with those back in the day. But I think it's really important to at least have these 2 and start moving on beyond those. Quite a lot of simulation in this area, especially along the harmonic balance line or periodic steady state, is, the mainstream companies have done a lot of work over the years with a lot of customers. I can't count, it's probably uncountable man hours that have, man years actually, that have probably gone into debugging and improving that code. So there's a challenge here, but the cool thing is we're starting fresh and we can be smart. So I think this paper by Kaxman, which I believe is, I think it's a 90 nanometer CMOS, is a really good paper because it was incredible linearity, and also represents the kind of complexity you can do, and where CMOS hits a kind of a sweet spot, right? So the cool thing about this paper is they go through the derivation of the system requirements, and then that's rare, because that's also another barrier, is sort of knowing what the system requirements are if you're a circuit designer. These are LNAs, they're variable gain. They go into a mixer. You can see there's more than one LNA for multiple bands and to combine into each mixer. Then at the output of these INQ mixers, you go into a low pass filter and maybe some additional variable gain in the ADC. There's DC offset correction is also needed in the very popular direct conversion architectures. So when you're talking about a direct conversion RF receiver, there's a low noise amplifier. That's this guy. And that sets the system noise figure. And it sets the frequency response against unruly antenna reflection. What that means is you better have a good input match, not to for power transfer, which is commonly assumed, but because you need to control the frequency response against an antenna that may be ill-behaved, and then it may be ill-behaved at a long delay through a cable in the product, you know, that causes a lot of phase interaction, which can then cause ripple in your transfer function from the antenna to the baseband. You know, the mixer translates RF so that the modulation appears around DC. It that typically sets the linearity. Now mixers, a lot of folks are trained that they're introduced to like a square wave, you know, detector or something like that in school, and they think that mixers are nonlinear inherently, and that's how they work. They don't. These mixers are passive FET mixers. You can look in the paper to see them, and you know, it's really a linear circuit, but it's periodically varying with the local oscillator waveform. Okay, so anyway, that's a very important point. Now, okay, so you can do an LNA. You can't really measure a mixer by itself because its input impedance actually depends on the source impedance that you bring to it, and that's a property of time varying networks. So you don't want to measure a mixer directly, say with a network analyzer. I know folks try to do that and everything, and under certain assumptions, it's okay. I think when you're time constrained on an open source world, and you don't want to, you know, it's your time, your nickel, and all these things. I mean, I don't know. For me, it's just you want to know what you're dealing with, and the thing that you can measure is the LNA by itself, and the LNA mixer, and say transimpedance amplifier, mixer termination amplifier. But one of the huge problems, of course, with receivers is that they have to be low noise, but they're also really fancy electronically tuned filters. And because you get these huge blockers that are undesired channels, and the bias noise is upconverted and degrades the noise figure of the desired signal. That's a simulation challenge that I think we need to try to address. I want to talk now about S parameters, and I'm going to do an unusual introduction to it. So if you just consider a really simple circuit, just a resistor, and you say, okay, I want to study it and put a voltage source on there. You know, when you put a voltage source on there, the voltage on the load is known. And analogously, when you put a current source on a resistor, you know the current, you know, and you can ask what the voltage is. But the question is, when you know, both those sources are infinite power actually. So, meaning if, you know, if I say this voltage source by itself produces as much power as you want, and that's not real. Okay, that's an idealization. So typically sources have an internal resistance, and then, you know, in the RF world, we think about this thing here as a port. It's a concept that you know, sometimes we don't draw the voltage source, but it's got a characteristic impedance or resistance we call R0, let's call it that. And then let's just draw two things, I'm going to call them A and B, and to distinguish them from voltage and current, I'm just going to make them a wiggly line. And it's, you know, but what do we know about this circuit? One of the things that's interesting about RF, say, versus analog design, you know, in analog design, you either go voltage mode or current mode. In RF design, you need to put voltage and current on the same footing. So the way we do that is kind of interesting. But let's just say, okay, this circuit here, if I compute the current, you know, it's just Ohm's law, and you know, so some of these two resistors is the voltage divided by that resistance. And then the voltage is a voltage divider. Okay, but let's just define this thing that we're going to normalize the voltage and current by the square root of this resistance over here. And then substitute in, these expressions and simplify it. Well, A, this thing I called A, that's independent of the load. So it's kind of cool because now I've got a thing kind of analogous to the voltage and current that's for a finite impedance or finite power source, it's constant. So if you then say, well, what should B be? I'm going to jump to the answer and not justify it, but do the same idea of normalizing the total voltage and total current and taking the difference. And if you work out what that looks like, it's here. I'm using some symbolic analysis tool here in Mathematica, which I'll talk a little bit more about later. But it turns out that okay, this is the definition of the reflection coefficient. ZL minus Z naught over ZL plus Z naught, and that's something that anyway, this equation in its impedance form, you just carry that around. You've got to know it, remember it, but you don't have to go into traveling waves and a lot of obscure stuff to get to this. There's a book by Balabanian, Electric Network Theory, that I don't have in here as listed as a reference, but he goes into S parameters as a network theoretical concept. So as opposed to a traveling wave thing and all that. So in general, the load can be complex. So we call that Z, because that's going to have a complex part, imaginary part, and a real part. R0, some authors venture into the territory of making that number complex, and that's a bad idea. Complex normalizations, in my view, are a bad idea. So I recommend against that. But what's very cool about this reflection coefficient equation is it applies to 2 ports and more if you just convert to the matrix form. So, in this way, the reflected waves are column vector. This is for port 1, this is for port 2. And the incident waves are a column vector. And then gamma is replaced by a matrix form, and then we call that the scattering matrix. So why do I care about S parameters? Well, one of the things that people do is they want to do impedance matching, right? So it means, we know that A is really just a function of the stuff over here, so I don't need to draw it, but I don't want anything to reflect back. And one way to think about that is getting conjugate match over here. I won't justify that, but I'm going to have a lossless matching network that's going to present the conjugate of what my load is. It's very cool in microwave engineering because some of the circuits are really hard to analyze, and you can take advantage of historically people took advantage of the fact that the scattering matrix for lossless networks is what we call unitary. So that really means, hey, the incident wave is reflected or transmitted but not absorbed. And then it's also the S matrix is for passive networks is reciprocal. So that means that whatever happens going this way also happens going that way. There's no weird things for non-rest, that's going depending on the direction. And so that implies the S12 and S21 are equal. And then, hey, if I'm trying to do a matching network, I know what I want S11 to be. It's that conjugate. And then if you work through the math and apply these things, you can say, hey, my matching network has to have an S matrix that looks like this. And in this form anyway, the insertion phase of this network is a free parameter. Again, I'm using a little bit of Mathematica here, but it's really easy to do impedance matching now with this, because you can convert this to a pi form, which is available from the Y matrix, which is a form of that matrix reflection coefficient idea. And then once you know the admittances, you can say, oh, that's a capacitor, or that's an inductor, And you can do something like this over here, which is I'm showing that at the frequency of 7 gigahertz, and I chose the insertion phase of 0. But if I want to match basically 0.88 or 0.9 to and an angle of minus 158 for the reflection coefficient that I'm trying to match to that impedance there, I can get those numbers out. Smith charts are interesting for visualization, but they are not the way, you can use modern techniques to come up with your matching networks for single frequency. And then, for broadband, it's a whole nother story, but I really find Mathematica useful for that theory of operation. And in particular, there's a tool called Nodal that I'll talk about again. Now let's talk about VNAs. This is, I found this in the garage. This was something that Doug Ritting did in 1982 when it was, when Hewlett-Packard was the main game in town for vector network analyzers. And in this, he talked about the so-called self-calibration techniques. And actually these were precursors to the modern techniques that we use. I bring this up and emphasize it because early in my career, knowing what our transistors really were from an S parameter point of view was super important. And we actually ran circles around our competition by focusing on this. So we did some stuff with network analyzers of the day, but we applied this. It actually wasn't available in the network analyzer itself. So we had to do what we call two-tier calibration. But the basic message here is, hey, you've got a imaginary perfect reflectometer, which is something that looks at these A's and B's. And I'm not going to go into that, but there's directional couplers, directional bridges that can do a pretty good job of separating incident and reflected waves directly. So that's cool. So if you combine a pretty good reflectometer, dual directional reflectometer, whatever you want to call this thingy here, and you have a really stable frequency generators, phase lock loops, which came in actually around the 8510 timeframe, HP 8510 network analyzer for those who remember those days. And you got to hang out the really stable phase of your network and have a really repeatable switch over here. So you can take a pretty good reflectometer and you can make it perfect by determining the error network, because it's not changing with time. Now, in reality, temperature in the room is going to have an effect, especially if you have long cables. But that's the key, is no drift. So one of the points I want to make about the architecture of the network analyzer is you need to measure the switch. Okay, because it's not the same in see when you are looking at S11 exciting port 1 over here, you've got to put the switch here, okay, and then you're going to see what reflects back, and you're going to see what comes through, right? Get it out here. But when you switch it back, you can do the same thing in S22, but see, the problem is if you don't consider the whole system up front, you're going to miss the fact that the symmetry of this thing is not going to be exactly the same. Switches aren't perfect, just like the directional, the reflectometers aren't perfect. And so you need to measure actually that reflection off the switch, and that requires an A2 over A1 style measurement, which is a bit odd, but that's why you need a 4-sampler architecture. Well, and I bring that here, just gotta move along and all, but I think it's a very important thing to realize. And so for these open source VNAs, it's great if we can develop those with the ability to do these self-cals. The importance of the self-cals are really that they don't require any detailed knowledge of complicated open circuit capacitances or short inductances. I see that all the time, and I get it, but it's not necessary. You need to know your short a little bit. You know roughly where it is, but you don't need to know what it is. And shorts are better than opens because opens tend to radiate. So here's an example of an open source VNA that I bought last month. I was really happy to learn that a 6 gigahertz VNA open source came available, and it's shown here. You can get it on Amazon for, I'm not going to quote the price because you can go look at it. And I've, you know, it's completely open, which is what it means is that for folks who are interested and curious, you can maybe move the ball forward, you know, on doing cool stuff, right? So, but certainly you can make some measurements. And I've begun using this unit, and I've calibrated it. I've made an antenna return loss measurement, you know, a 5 to 6 gigahertz antenna input impedance. I got a good number. You know, but I'm not saying more about this VNA, but it's there. And the, you know, it's complete with a Google user group, so that's kind of active right now. And when I had a kind of a silly bring up problem associated with having enough hefty enough power supply, it's a 5 volt need. You know, the developer emailed me within a half an hour, or responded within a half an hour on his little Google group there. But you know, one thing is that open source is doesn't mean free. I mean, what it means, right? I mean, it's totally worth it for me to pay some money, you know, for this, because what am I? It would take me, you know, I mean, I suppose I could like, you know, try to have somebody go build this for me, but it would never be as cheap as what it's offered for me, plus my time. So, so open source doesn't have to be free. Open source is freedom, right? I think I've seen that on some folks' websites about open source. But anyway, coming back to the open source VNA calibration, just some recommendations and ideas. You know, the commercial calibration of choice is line reflect match. Okay, so that's one of these self-cal techniques. Architecture for samplers, I talked about that. There's a trick I did way back a long time ago, which is if I'm trying to do something onto a semiconductor, in that day it was gallium arsenide, but you can't you know, get a good resistor. In fact, the ISS standard that you'll get with probes, and those aren't cheap. I mean, you're talking about you know, it's over $1,000 to set yourself up with this, but could be affordable to some. It's not $10,000 for the probes and ISS standard, the impedance standard substrate that they typically give you. But anyway, if you want to get directly onto silicon or semiconductor, that was GaAs in the day, I did this thing where I thought, well, you know, if I design the resistor low, it's pretty easy to get it to go up, and I could tweak in and get it precisely to 50 ohms by biasing the resistor and you know, using DC to prove that it was at 50 ohms. So you don't need to do the trimming, laser trimming that's done on these ISS substrates. The other thing I wanted to say, and I actually wanted to do a little bit more, but on this, you know, there's a lot of stuff out there on calibration. You know, look up Dylan Williams and in the IEEE and at the NIST website, and you'll get some very interesting, sophisticated techniques. They may be a little hard to apply or hard to wrap your head around, I should say, but you know, this has really been developed as an art. The other thing is this paper here, which kind of put into the IEEE literature, this basically some of the things that Doug Ritting observed, and it generalized it. There's a whole bunch of things that are derivatives of these self-cal techniques And if we could do a self-cal technique that allowed fixed position of the probes, that would really lower our costs. Okay, I showed you earlier the Skywater PDK information. Oh, anyway, maybe I should stop here and see if there are any questions. Does anyone have any questions? No? Okay, I'll move on. Am I right? There's no questions? Tan, anybody? Anybody still there?
I don't see any.
Okay.
I didn't see any raised hand.
Okay, so I talked about how Skywater's PDK is open. You can download it yourself to, now. It's using BSIM4, and BSIM4 is pretty good, to be honest. And it was intended originally for digital, and the digital guys do models that run fast because they're running with a lot of transistors, by definition, if you will. And we've developed a lot of good chips on BSIM4, okay? But I think, so I'm not saying this is a stopping point, okay? You can design with BSIM4 core models and then extend it using some measurements with S parameters to extend those models, for RF. Typically what we do, I guess I haven't talked about that much, is, you've got the core model, which has been, based on DCIV, CV measurements, etc., BSIM4 methodology, extraction methodology, and then you use the S parameters to add parasitics and refine those parasitics. It's typically not sufficient to just rely on the compact model. But there's another deeper issue that is important if we're going to spend our valuable spare time on this, or if we're venturing off and we want to be successful. We don't want to have things that are fundamentally flawed if we can avoid it, right? And that's where this this issue of symmetry and the Gummel symmetry test came in. And in 2004, this has been known for a long time, but it takes a long time because modeling efforts are very extensive. So anyway, this article here by Bendix talks about how there's unphysically asymmetric model behavior around VDS equals 0 in many of these models. And then, so at least when you're operating around VDS equals 0, you could expect some problems with distortion tests. This is a current thing, and it's also a capacitance thing. I was talking before that passive networks are reciprocal, right? If there's nothing, if you have a passive thing that you're not really supplying power to, let's say, you can bias it, but you're not supplying power to it. It's going to be, it must be reciprocal physically by just from nature and fundamental principles. So that's something that's a problem too. And on these capacitances, and BSIM6 is a relatively new model, but it's established. It takes care of this. There is a 5-step non-iterative extraction procedure that's been published in 2012, and you take DC and S parameters, and there's 5 steps. And one thought would be, hey, maybe we could play back BSIM4 for DCIV and supplement with S parameters. That's something that an interested person could do with some focused devices that are getting his RF circuit path, and do that and get going. I was involved in an entrepreneurial effort in 1999. And we did not have models from the foundry. We were with the tier 1 foundry at the time, and we did our own measurements to focus on the devices we were interested in and get going. Later on, the foundry came in with their own excellent characterization and models, but it's not clear that we would get that in these open source PDKs. I want to talk now about noise, and this seems to be something that's an add-on from SPICE world, and so it's in all the RF simulators now, and I don't know if it's in the target open source simulator. There's one from Sandia Labs called XYCE, XYCE, that I'll talk about on another slide. And it does harmonic balance, the basic one, and it does, according to the documentation. I have run an early version of it, tested that it's functional, but the noise correlation approach is what's needed for kind of well, I'll say it this way: it's not absolutely needed, but it's what's being done in the commercial, sort of RF simulators. And what it is you can take any linear network now, active or passive, and non-reciprocal or whatever, and I'll leave out time-varying network for now, although the basic concept applies in a way, but that's a little more complicated discussion. But the basic idea is you can take your network and pull out the noise sources. So no matter what's in here, in your sort of real network, with resistors and GMs that have noise, etc. Transistors have noise, and I'm talking thermal noise here primarily when I think about this, but I think it's true in general. Typically what we do is what we call the correlation Y matrix, and this is because you have a short circuit current at the output and the input, and they have a complex correlation coefficient. So that's common in device theory literature for some reason, and it's also convenient in circuit simulators. So the Y matrix approach is easy to combine, I think, into more complex networks, but I think correlation Y tends to be what the simulators use and report. They also report the classic noise parameters, but behind the curtain, correlation Y is happening. There's you can do any type of source, actually, voltage or current at input or output. I mean, all combinations I think are legal. And so one of the ones that I wanted to mention, because I haven't seen it, and it's super convenient and it helps you think about this stuff, is correlation H. It's convenient for FETs, right? Because the input circuit on a FET is a series RC, and it's really the R that's generating a voltage noise. And when you short it with this, you're going to get a frequency dependent thing. But if you open circuit it, it's just you're going to get the voltage of that resistor, to first order. So the other thing that comes in is people. I want to bring up that there's a lot of confusion about this because it could cause churn on the noise model of these FETs in the PDKs, the open PDKs. So we talk about induced gate noise, and because what's happening in a FET is, there's a linear region near the, this might be saturated of the channel up here, and this is a linear region, and it's like, okay, fluctuations down here, that's going to cause something to happen out here, and they call it induced gate noise. I mean, that's the term. So I looked some time ago at a heuristic idea because I was very puzzled by correlation, right? What is the correlation between, say, IDN and VGN in a FET? What would it be? And there's a lot of people going, oh, you got to get it experimentally and all this stuff. Well, a uniform RC network can form a heuristic model for a FET, okay? And surprising things happen. So I want to explain that. So the noise of this distributed resistance, which appears at the input, okay, open circuit voltage, and at the output, short circuit there, and those are non-zero, but their correlation is zero, even though they're coming from the same place. And that's a very odd thing to say, but it may be because we think of correlation as being associated with place, right? Like, hey, if both things I'm measuring, okay, fluctuations I'm measuring at two different places are coming from the same place inside, I would expect them to be correlated. This is a wrong intuition, and you know, you can prove this if you have access to an RF simulator. But actually the formula for what a URC is, it's S parameters and Y parameters, is something we can find in the literature too. So anyway, it kind of looks like the input of a FET. This is the S11 of that structure. I had to ground dereference this thing because this is the ground node in the simulator. You have to pull that node off of ground, and it's kind of built into that's node 0. So anyway, what I've shown here is that indeed the voltage noise of this widget thing, you know, that I showed on the previous slide is something, half a nanovolt and RMS, and you know, a few tenths of a picoamp or a tenth of a picoamp RMS on the short circuit current. But the correlation on what I call correlation H here is that this is the numerical noise floor. So because this is 14 orders of magnitude on this graph here. The correlation Y parameters have, you know, strong correlation. So if I was to be looking at the short circuit currents, you'd have a lot of correlation. So correlation is about how you look at something, which is a bit odd. So I'm going to go into some other misconceptions, but if there's any questions, feel free to interrupt now. But I'm just going to move on. Common misconceptions about silicon RF design that I've found, I would like to just share to the community that's going to tear into this stuff and be curious. And I just don't want to, you know, I don't want my field to be so esoteric. So I'm going to dispel some misconceptions or upset people. I don't know. Maybe nobody cares, but you know, this idea of eddy currents under inductors is actually wrong. And I'll point to something on that. It's also a misconception that microwave stability factor, which is something that's in the microwave textbooks, proves stability. It does not. You know, I've already mentioned that it's common that mixers are nonlinear. They're not. Mixers are linear and they're time varying. That's how they get the frequency translation. And then, you know, the other common misconception is you can't get really high Q things on RFICs. So the first one, unfortunately, I have to point to a webinar that happened in 2014 that I attended, and the you know, Jim Raudio and Joy Laskar did this, and Jim Raudio is the founder of Sonnet Software. And he says here, everyone knows that silicon RFIC inductor loss is mostly due to inductive coupling with the substrate. Everybody knows it. You see it I mean, I hear it at work. But you know, the current is inductively coupled with the substrate. It will flow parallel to the current flow in the inductor, but it'll be opposite direction, okay, because of the way the magnetic field and currents work. And so that's going to screw up your inductor. In that presentation that I attended, which unfortunately is not still available on the web, they analyzed, and with Sonnet, you can visualize substrate current, and they found out that it's wrong. They proved that it's electrical, okay? So, and for me, you know, silicon permeability is mu0. There's nothing special. Eddy currents come in when you have high permeability material. So anyway, that's just something I'd like to share, that, you know, in the open source world, let's be smart and not say eddy current. We do have substrate losses, but they're electrical. The stability factor, you know, it's just got a wrong name. It's a very useful thing. It tells you whether if you put reflection coefficients that have a magnitude of unity on the input of a network, will the other side, looking into the other side, will you see magnitudes less than unity or equal to or greater than unity? And that's a very important thing to do, but it's got nothing to do with stability. Well, yeah, it actually doesn't. Struble and Platzker back in 1993 were working on pseudomorphic hemp PAs, and they were K-stable and they oscillated. So they came up with another method, which is basically a Bode method for each GM source. It's pretty cumbersome. What I showed here is something from a workshop that, I show that mu and mu is a modern stability factor. You only need one or the other. K and B are a little bit older, but you find them in a lot of the commercial simulators. But this thing actually does oscillate. I guess didn't show the part here that shows it's oscillating. But if you run a transient sim on this thing, this 180-degree transmission line feedback, it will oscillate. Practically speaking, what folks do actually is check stability with transient simulation, and you either supply a step to the you step to supply, or you do a current impulse, or even a current impulse dipole at devices you're concerned about. So you can check in the time domain. In mixers, CMOS, unlike bipolar, makes a great switch. So most modern CMOS receivers use 25% duty cycle driven passive switching mixers, and switches, when they're in their either state, they're transitioning actually too. They're linear. They're not fundamentally nonlinear, but they're time varying. So it's a time variance that does the frequency conversion. For those who would be new to this field, there was a kind of some interesting breakthroughs 10 years ago or so that, 15 years ago, I was, kind of stumbled into this myself, where you can, because the passivity of a passive mixer, or the reciprocal nature of the passive mixer, the baseband impedance can be seen from the RF port. And what that means is if you have capacitors on the baseband port, that capacitance is translated up around the LO frequency. So Mirzai and Darabi published this analytical expression, because it's pretty hard to figure out what's going on. There's this little shift here, and that's problematic. There's ways to correct for that. There's stuff in the patent world on that. But the basic answer is you can pull a tank that you might have here and pull it low. That is possible. The question is, how do you do it? And there is a patent in the literature that you can find that use a technique that injects DC and then looks at the voltage, and that gets you pretty close to centered. But you can see that these slopes are governed by the size of the capacitor here, and this center frequency is governed by the rate at which you're driving these LOs. So you can get really high Qs. Okay, I want to talk about the open source simulator Zeiss. I had hoped to get a little bit more done on the validation, but I've installed on my own personal machines the 7.3 release, which was just recently released, and it does, according to the documentation, it does linear S parameters, it does harmonic balance. I don't know about RF noise, and I don't know about small signal mixer analysis. I think no, but it's really important that we have like example circuits for the open source simulator world, that that we get the folks working the simulators to analyze, and so that's kind of a to-do. With the open source PDK from Skywater, there's nothing stopping anyone from doing one of these passive mixers and with that design kit, and then looking at what it does and comparing it to expectation, at least. So so there's that. So in terms of a general EDA tool design flow, At the early phases, you know, MATLAB is common in academia and in industry, although Octave is an open source version of MATLAB that some colleagues have used in the past. I've not used that much. Python, been involved in using that quite a bit. But my favorite tool is actually Mathematica. Alfred Riddle, his email address is listed there, wrote some years ago a tool called Nodal. It's available if you email him. He wants to keep track of users. It's not completely open source, but it's very low cost. And for me, it was free. I don't think he's charging money for it, and I recommend it. I also recommend Mathematica, which, you know, for personal use, it's a very low cost yearly use for what you yearly cost for what you get. The schematic entry being used by the pioneers in this world of open source RF is XSCHEM, it's called. It does require compiling on your Linux machine, so that's a little bit of a barrier for me, where this is, you know, not my day job. I like install binaries and all, but anyway, this is what Thomas Perry, who submitted an RF design on these MPWs, these Google-sponsored MPWs, used. And so, in the interest of design reuse, and you know, which I want to take advantage, or anybody would want to take advantage of what's been done before them, and they can perfectly download it. You know, which I did. But you know, you want to do that. Now, he did not use Zeiss because there was an issue with units on the earlier version. I'm hopeful that's gone now. He used ngSpice, which is another open source circuit simulator. But I really think for RF, we got to focus on Zeiss. I don't know of another one that does RF. I have a low cost tool that I bought called Tina, which has an RF version, but it doesn't do harmonic balance. It does switch mode power supply, periodic steady state. I've not really listed it here. It's probably an omission, but that's a low-cost tool, Tina, T-I-N-A. For electromagnetic simulation, I mean, you know, Thomas Perry did an inductor in his design, and he talks about it in a YouTube video that you can listen to. I think he used acidic, which has been around since the late 90s, out of Berkeley, Professor Nick Nijad's early work, I think, as a part of his PhD or so. And or you know, came out of Berkeley there, and it's still available, but we're not going to get there without an electromagnetic simulation, guys, because you've got to account for things beyond just the inductor. That's my experience. And also, you know, an inductor tool is not it, because there's so much creative things you can do in magnetic fields. So I really recommend that we go and develop electromagnetic simulation. Now, Sonnet has a freemium model. The Sonnet Lite is free. It's constrained. It's probably over constrained for this problem, and because it's so limited, they don't ship it with a GDS import. You know, because they just don't want people getting frustrated importing things that are not simulatable in that constrained EM simulator. So, but they do have a freemium model. You can do a limited term license. It's not super cheap, but it's not outrageous either. Then there's OpenEMS, which you can find on the web. I did. It's full. It's a frequency. It's a finite difference time domain. It is open source, but it's not 2.5D, and it's probably a lot of work to get it to go. But that would be cool if we develop some 2.5D, what we call 2.5D planar style tools that were open. And when it comes to layout, there's KLayout. A lot of folks use that for GDS viewing, you know, just in the IC industry. Magic is the open source tool that is part of the Open EDA world. You know, you can see that in the webinar from the Solid State Circuit Society. And apparently you can do DRC and LPS and PEX somehow. I mean, I'm not run it myself. I don't mean somehow. I think, you know, I think it's doable. And I was thinking about this, you know, back in 1998 or so, when I was running 180 nanometer when it was new, you had to have the best tools, otherwise it was going to take you forever. Now it's 20 years later, and CPU speeds are really high, and so maybe we can make up for the fact that, you know, software hasn't been optimized by thousands of users, you know, feedback over the years, let's say. So it's an interesting thing to see how far we can go with these open source tools and how fast things will be, just because we can use open software, which might not be as cool as the professional stuff. Well, I mean, why would we expect it in the early days anyway? And but we're running on a fast machine. You can get liquid cooled 16 core machines. They're not cheap, but you know, if you're a gamer or something, you might have one. So one of the things about the flow is it's always good to look and see what others have done. And there was a YouTube live stream with Thomas Perry about, you can see at this link, and he talks through how he did his flow. So the collaboration roadmap, in my view, has to start with low cost S parameters, and yes, on wafer. And we can really lower the cost if we can figure out fixed position calibration techniques, right? It's expensive to get something that maintains planarity when you're moving it back and forth to adjust for the device and the calibration standards. So I believe that's possible. We need the model hardware correlation for FET devices, and then what we can do in LNA, right? And then certainly if you put it into a PCB, you can measure its noise figure pretty inexpensively. I actually purchased an old HP noise analyzer on eBay for $350. It was cool. There was somebody who was done with their noise diode. Those are expensive, so I was lucky to get one of those. But you know, with a mixer and a local oscillator, but you can get a demo board of some kind. But you know, you're into making noise figure measurements up through 6 gigahertz pretty easily. One of the thoughts I had was correct by construction layout. So challenge I worry about is we've got so many, you know, these processes are developed for digital, and they can do a lot of density. That creates a big verification challenge, and we got lazy, right? We run the verification tools over and over and over again, rather than just kind of trying to keep it, you know, like, hey, just try to be careful and don't run it so often. Now, eFabless runs caliber tools, DRC wise, you know, before on your submission. So, you know, so that's going to be the golden rule deck. And Thomas talks through that a little bit, I think, in his talk. But you know, you get it as close as you can with the open source stuff, and then you submit. You might get oh, you got to fix this kind of feedback from eFabless. All right, that's all I have. Would anyone like to ask a question?
Thank you very much, Tom.
Okay, so it looks like there's a couple of hands raised. Am I right? So Adam, let's see.
Hello.
Hello.
Can you hear me clear?
Yes.
Okay. I have been studying RF like for 8 months or so. So please bear with me with my question. Okay. Sure. The first question is the mixers are linear. I didn't quite get it because whenever or wherever I read about mixers, they state that they are nonlinear and we care for their linearity, like intermediation, the third intermediation or so. So how in practical life is linear?
Well, yeah, I wanted to have a little bit more on that. I'm afraid I don't have a good diagram, but I wonder if you can picture just a switch, you know, single pole, single throw switch,
Yeah.
connecting, you know, between two resistors, right? And it's switching at a rate of the local oscillator. So very fast, switching at the gigahertz rate. That thing down converts when you choose on one side of that mixer, you know, you choose the low frequency term, because you're going to get sum and difference terms, right? But if you AC, you know, put a big cap, right, on one side, you're going to only see like the low frequency stuff on one side of that switch, because you'll get the difference frequency, right? So because you're switching at the LO rate, but your RF is not quite at the LO rate. It's a little bit off, you know. Think of it that way, right? There's modulation. So in general, there's energy close to the LO, but not right at it. So anyway, that thing is a mixer that I just described. That's not nonlinear. And you can say, well, how does it make frequency conversion? It makes frequency conversion. One cool way to think about it is that you can think about that mixer is kind of multiplying as kind of a multiplier. If you think of a polarity reversing switch, okay, this means a cross-coupled switch, polarity reversing. You can think of that as multiplying the input signal by plus and minus 1, right? The way you can observe how much frequency conversion, or the fact that it's converting in frequencies, you can recognize the fact that multiplication in the time domain is like convolution in the frequency domain.
Yeah.
There's nothing nonlinear about any of that. I know you see it in the literature. You see a lot of things in the literature, and that's one of my main purposes here. I'm so glad you're here, Adam. 8 months, you know, because it's like, look, I can say I protect the innocent. I want to be very fair to people and not be, I want to just talk about ideas, right? So, but it was very common. In fact, when I got involved with CMOS RF, I had worked a lot on FET mixers and gallium arsenide, and I came into a company, you know, that had very experienced cellular folks, and they were pretty sure that the switching mixer wouldn't work because everybody was talking about these bipolar, you know, sort of multipliers, linear multipliers. And that's just wrong. I don't know how else to say it. That idea is wrong. So, don't read that. Just put that aside as my recommendation. Yeah, you really want to keep track of this idea of what kind of system are you dealing with fundamentally. Now, of course, when you drive the input of the mixer hard, okay, it's nonlinear, right? Because actually what happens is the RF signal begins to affect the switching times because it's also influencing the gate of the transistor, right, or the VGS, the turn on volt, you know, the control voltage of the channel. So the mixers are the weak link in the chain for linearity, but they are not fundamentally nonlinear.
All right. Okay.
Any other questions?
I have a second question about the stability. When I read it before, like there is some sort of equation like K equals some sort of S1, S11, S21.
Right.
Yeah. Is this like correct? Like the stability is like you you elaborated like it is not the main thing. Like it's still oscillate, and like the equation is there.
Yeah.
You know what I mean? Like,
yeah. Let me see if I can quickly do something here. So the equations are nice, but you want to develop an intuition for things. Okay.
Yeah.
And you know, it's not like K is not useful, but if we have a two-port network here, all right, I'm not going to draw all the ports, I guess. It's well, I got to draw a little bit more, I guess. But you know, we've got a port over here, and, a port over here, a terminal anyway. Yeah. And by the way, another thing to be careful of is, you know, we're usually talking about what our I don't know what you call them, are the original inventors of our field called three-pole networks. We're not usually talking about independent two-port networks. Okay, so that's another mistake that's made often, where you think you can put two terminals anywhere on this box and then describe between those two ports, and that's a complete description. That's not true. This is what a two-port is it's really three-pole, because otherwise you don't have a complete description. And that's kind of, it's not as important as what I'm going to describe here. So let's say you put, let's say this is the reflection coefficient space, and this is a unit circle. Okay, we can be anywhere inside here on this load. All right, and then let's say here, this is the unit circle on the input, and we're looking at the input reflection coefficient. All right. Now, K factor, and mu, if they are good, that means that, that means that this disk maps into something inside here. Okay.
Yeah.
I suppose if it's lossless network, it would be around here. But if it's an amplifier, you know, it could be that it has a lot of forward gain, but not much reverse gain, right? So we could have a circle that's smaller over here. But the other thing that can happen is, so what K factor tells you and mu is that something like this is going on. So when the input reflection coefficient goes outside the unit circle, that means it's a negative resistance.
Yeah.
And it's kind of dangerous. That's cool. You know, the analog design paradigm doesn't have something equivalent. Okay. But it's really the analog design paradigm of like return ratio that you need to do stability. So this is what K factor tells you. And, you know, just keep that in mind. You know, the formulas are one thing, but what is it really telling you? It's about these circle mappings.
Okay.
Yeah, and it's something one can prove that, you know, in the S parameter world, circles map to circles. So no matter what, you know, if I put a circle load over here, I'm going to get a circle on the other side. It's just going to be shrunken, or it could be bigger, and it also could be turned inside out. That's another weird thing, but it can be displaced. So, and you see that a lot with, you know, noise circles and all that. Okay.
Okay. Okay. Thank you very much.
Welcome. Good luck. Okay, so let's go with, is it Jehan?
Yes, good morning, sir. So, sir, I have to apologize because I'm not very strong in this field as well. But when you were talking about the models of BSIM, the Berkeley models of 4 and 3,
yeah,
you said that we cannot imply the analysis on it. So does that mean that, because these models are basically models we make to describe the MOSFET, so can't they be corrected so that we could do the analysis? Or is it that the nodes, like for example 130 nanometers BSIM 4 cannot be used at all? Because I think you can correct models using Verilog and all, right?
Well, so this is one of those, what domain are you going to apply these technology to? And when the BSIM models were originally, the BSIM line was originally invented, they were really focused on digital, and analog, where you don't see a lot of the kind of the RF effects, right? Although probably the symmetry test causes some observable issues that you might identify in an analog circuit. But no, I didn't mean to. I tried to sort of temper my remarks. I've done chips with BSIM4 at 90 nanometer that work fine. Okay, and it's just that we have a known issue in the BSIM4, and since that time, this is the early 2000s when I first got involved in CMOS RF, and in my previous companies, we said, gosh, let's do something better. There was these so-called surface potential models, so-called, and those we knew were better, but it was a lot of work for a production company, product company, to do all the modeling work associated with switching to a new core. So when I say core, I mean like core model, BSIM, there was EKV, there's MOS 11, there's a bunch of models, but in the BSIM family, Christian Enns, who was the E and EKV model, he got up with the Berkeley folks, and he put in some good stuff so that we could have this reference this paper here, and so all I'm saying is that my recommendation is not to fix up the BSIM4 with Verilog A. I hear you. If we're going to do work on changing anything in the core, I recommend we look at this BSIM6 idea. But BSIM4 with some RF parasitics, more careful for specific layouts, that's perfectly functional, perfectly good enough to do excellent things because we did it. Does that make sense?
Yes, sir. Thank you, because I was a bit confused on that.
Yeah, I would like to see, like, if hey, it's not like a company, and but we're collaborating, and I want to. This is not proprietary information. This is just knowing what to look for in the literature and having the experience of living these things, and I just want to share that with you. So anyway, I think we connected on that, and yeah, the modeling is very difficult, but we don't use all the transistors in RF, right? We're going to use short length. We're going to use NMOS mostly. So we can pick a few and maybe do something like this procedure here. It'd be a great project for a student or just someone who's curious about this. It's not this paper. They've showed doing it and all the equations you need, and you can do it with an S parameter simulator. You can do this with Zeiss. You could simulate what the S parameters are of your BSIM6 and then compare it to the measurement and follow their procedure. I'm oversimplifying. Modeling efforts are very tedious, but it's something I feel we could do. Okay, we're gonna go to Paul.
Thank you, sir.
Hi, Tom.
Draxler. Hey, how are you, Paul?
Good. How are you doing?
Quite good, thank you.
Good, good. So, very good talk. I wanted to expand on something or ask you a question, I guess. On the reference to Platzker's work, have you also looked at what Almudena Suarez has been doing in that same realm of looking for internal oscillations within larger RF power amplifier structures in the stand tool? Are you familiar with those things?
Is that for linear circuits or is that
Nonlinear.
driven? Nonlinear.
Nonlinear.
Yeah. So nonlinear is a whole nother animal.
Well, Almudena Suarez has looked at basically it's related to Platzker's work.
Oh,
And she does, she's written a book and put together quite a bit of material on it. They're related, but they're different. You know, Platzker looks at Bode plots, or Bode, it's kind of an expanded Bode
Yeah.
approach. What Almudena has done is she's looked at how one would break a particular node within the circuit and look at the onset of instabilities.
Okay.
Watch the bifurcations. Watch the nonlinear behavior turn into bifurcations and then turn into oscillations. And the tool that does that is Almudena Suarez. Suarez is her last name. I'll send you the references, but just for everybody who's attending.
Yeah. Do you think it's
SUAR AZ maybe? Easy. Yeah, that's right. SUAR easy.
Yeah, thank you for that, Paul. I just don't want people to be doing the wrong things with K, because
Externally you can get perfect K behavior, but internally you can wind up with loops that create oscillations, and so you just guarantee at that particular plane you don't have the K instabilities, but there could be other loops within the structure that cause instabilities, and it's an easy trap to fall into.
Right. And for us, you know, by the way, I've known Paul a long time, and we've been colleagues in certain projects and stuff in the past. And so, yeah, thank you for that. The thing here is, you know, I see a lot of stuff with K factor on LNAs, and for integrated LNAs, you know, it's really a little bit wrong-headed to be using K. So that's really the message I wanted to kind of, I'm focused on the LNA mixer side and right now. And, you know, first of all, K, as we've discussed, it doesn't catch everything. And then the classification of circuits that it does catch has to be separately identified. So it's kind of close to useless, but I do point out that it does that thing about the circle mapping, which is, it's very hard to do that with, say, a Laplace domain and an analog idea. And so there's value. But you know, when you know the termination of your LNA, right, that's another thing. You know what's going to be presented to the output node of an LNA on your chip. It's going to be terminated in that mixer, at least when it's on. And so and I've seen a lot of designers who are more coming from the IC side as opposed to maybe the I don't know, the 3.5 world. We were all doing this K factor stuff, and we were paranoid of negative resistance. I had a friend who was designing an amplifier that had negative output impedance until you drove it hard. You know, I mean, it's like, is that good? I think that might be bad. You know, but and so I think one thing a friend of mine told me at RFMD one time is that, you know, you can just spend way too long focused on stability. Stability did catch me out on our first chip in a startup company. Then that was bad, and we didn't discover it, but we until kind of late. But we did it with a transient method. So you know, a former friend, or not, a former colleague of ours that, you know, I worked with his team, and they plugged into their whole approach, you know, the ability to do something like NDF, or maybe what the Suarez is doing, which would be a more modern version of it. But it's really a hassle, and it really is disruptive to design flows that aren't, you know, like the models and stuff, right? But you can do it, and So when I think we need to leave PAs, like really good, high power PAs that are super efficient and all that for down the road. I think that you can do a lot of things wrong in PAs, and it's not for I think we gotta be careful. But I do think we can do LNAs, mixers, receiver chains with what we have at hand in open source. Okay, Paul went on mute because I was babbling on too long. Let's go to Henry.
Hi, Tom. Can you hear me?
Yes.
Hi, Tom. Thank you for the presentation. Very informative. And
you're welcome.
I have one question. So have you tried other open source simulators? And to be specific, have you tried Quarks? QUCS?
QUCS, I have not. Does that one support S parameters? Do you know?
I think so. I think so. Yeah.
Okay. I think I checked it, and I could be wrong, but the Zeiss is the only one I know that does harmonic balance.
I see. Okay.
Now, when I was working in the 3.5 world, and some folks were doing RF in BiCMOS SOI or whatever, and that world was perfectly happy with PSpice, let's say, and using tricks to work around the fact that they didn't have certain things. And my feeling is we should be focused on the harmonic balance stuff, because that will have legs. But you can definitely do work with transient, right? It's just you gotta jump over those transient times, but the meaning like if you have to see something settle. But the real rub comes in if you want to measure the linearity of a direct conversion receiver, right? And you have a desired signal that's 100 kilohertz away from a 5 gigahertz carrier, and then you have a blocker that's a couple of megahertz away from the 5 gigahertz carrier, like I was showing.
Mm-hmm.
That's going to take a long time to do in transient, right? Because you've got to, so that's the fundamental issue. And by the way, colleagues at the time in the early 2000s were all, like you got to use power, periodic steady state because of the nonlinear waveform in mixers or whatever. That turned out to be not the case. And those same folks, 15 years later, swore by, the advanced specialty tools from the commercial providers, because there were some late comers, on harmonic balance, right? We had all the stuff from, it was actually Hewlett Packard at first, and then Agilent, and now Keysight. But then we had, there was a startup company called Expedient, I guess, and they had a tool, and that turned out to be quite good after a fashion, and it was acquired by Keysight and incorporated into their harmonic balance tool suite. But we used to swear by that tool. The cadence harmonic balance has gotten better and better, and so that's very good. The Keysight tools are very good, but it's really all about like stuff like this here, getting this right. That's a hard problem to do because you've got these, you've got to simulate, there's disparate time steps in here, because you've got the tone spacing, which is really small, microsecond maybe, and then you've got nanosecond, sub-nanosecond periods for the RF carrier. So your transient sim has to have the time step commensurate with the nanosecond, sub-nanosecond world, but you have to simulate as long as microseconds, and maybe a lot of those. So that's the rub. Okay, Kevin.
I just had a quick question about applying AI to RF design. Anybody doing
I'm sure lots of people are thinking about that. When you say AI, are you thinking the kind of AI that we have that can recognize images and stuff, that we train a convolutional machine, like whatever they
No, it's more like smart modeling, because space goes so slow. You can create smart models with AI.
I'm not familiar with that. Is there anything in the literature on that? Or
Bernard Woodrow. This means squares, adaptive filtering stuff, and adaptive control theory.
can you say the name again?
Bernard Woodrow. He's at Stanford.
Okay.
I would have put stuff in the chat, but the chat's disabled.
Yeah, we had a I thank you, Kevin, but we had a issue with Zoom bomb,
Yeah,
and it was really bad. So,
I couldn't raise my hand on my PC, so I'm sort of on a tablet as well at the moment.
Oh, okay. Well, anyway, did I spell it right? Is that? Can you see that?
It's WIDRO.
No, it's very interesting. I'll look into that.
I'm gonna look for the adaptive inverse control book, second release or something.
Okay. All right. Imran?
Hey, Tom, how are you?
Good. How are you, Imran? Nice to hear your voice.
Yeah. Quick question along the lines of harmonic balance. So in your experience, how do you compare the cadence harmonic balance capability with the Keysight's ADS harmonic balance, if you're looking at the latest version of both of these tools?
That's a good question, but I think I'd rather take that offline if you want to chat about it, because yeah, you get a lot of experience and this quirk and that quirk, whatever, and then but things move with time, and and in this forum I feel like I'd rather talk about it privately. So we could get together some. I also wouldn't put it in an email. I don't think that's fair. You know what I mean? Because that gets forwarded around. But I could relate some experience if you want to send me an email, and then we could set up a time to chat.
All right.
Anything else? Okay, Jeremy. Jeremy, I'm asking you to unmute. There you go.
Hi, Tom. Thanks very much. Hi. Just a very, very quick question. I see the main thrust of this is to develop the RF models, and now that's become more accessible. Roughly order of magnitude, how much time would you estimate it would take to actually iterate and generate a usable RF model? And what sort of magnitude of money are we talking about?
So, in my experience, what you do is you don't do a comprehensive model set. Okay, because there's a ton of devices in this technology. You can download this kit, and there's various VTs, etc. So you pare down and you choose kind of which devices you're going to use based on the existing models and experience in the literature, and then you would model those and over a limited geometry range. So this transistor here, it's an RF primitive, quote unquote, but it's way too narrow. You couldn't measure it, right? So you wouldn't like you got to be smart about it. So the thing is that I did this, okay, pretty much myself, with a colleague who was also from the 3.5 world, but it took us I don't know, a month or something. We had an Enritsu network analyzer back in the day, and a prober, and it's pretty simple. I mean, you're talking about refining RG, the gate resistance,
Mhm.
and some capacitance, adding some capacitance in. So getting a working model is not much at all. The trouble is, that instead of getting a new car, you've got to buy a network analyzer, and that's changed. So I think 6 gigahertz is high enough, especially if you scale the device up, right? You measure something that's easily seen at 6 gigahertz that has a reasonable trajectory, reasonable amount of phase on a S11. Not doing a really tiny device that's basically an open, barely, so I'm hesitant to say how much, and all that, because I can't extrapolate. But the big thing for me, Jeremy, was the 6 gigahertz VNA, which is, I've just started playing with it, and I checked for stability, and it's pretty good. You want to leave it on and stabilize the temperature for a while, probably. And it remains to be seen, actually, honestly, whether we can do good FET S parameter measurements on wafer as an open source community at all. Okay. You could go to a university or something, but that there's challenges with that because of availability, and I don't know, what kind of legal arrangement is implied when you show up there and do something at a university which tries to control its situation, right? But if you have a good, if you have a friend with a lab, that's one thing. Two, that can lower costs, and you could change your vector on this. But I'm thinking something that one of us could, many of us could do in our garage for, okay, I paid $600. I didn't say, I said I wasn't going to say how much that VNA was, but it was $600, Jeremy.
So you're saying basically the time elapsed is probably going to be the same, because you're still going to do the same tedium processes, but instead of spending 60K on a piece of kit, now you can do it for under $1,000. That's the sort of order of magnitude we're talking about.
Yeah, and I have, like manipulators are in that few grand regime, and you got what about a prober, but I don't know if I took a picture here, but this is you can see my screen. This is a prober that I got off of eBay. It has a probe card holder. This happens to be a Rucker and Cole's one that I used for 10 years. It doesn't quite work right, but it's good enough. It holds something parallel to the platen. You could put a die down here. But see, this probe card holder, you can plug that in, and then you've got if you've got a repeatable thing, turning these guys into RF manipulators, which is another option. I have a machinist friend who's volunteered if I tell him what I want, but that's kind of a nightmare. And so I'm thinking that we could use calibration schemes that don't require this changing in the separation of the probes, because that's where a lot of money has to go. If you look at those RF probe manipulators, they're not these DC manipulators, that kind of thing that you may have seen. So that's really expensive. So I'm thinking if we could innovate on the calibration scheme, and then use probe card holder. This is just a FR4 probe card holder, right? That's what I'm thinking about. That would be a minimum cost kind of situation and maximum cleverness.
Yeah, that is intriguing. It seems like we're heading towards the Arduino style of RF chip.
Yeah, exactly.
Which is massively accessible.
Well, Jeremy, I highly recommend listening to or downloading the slides for the April solid state circuits webinar if you haven't already. There's RISC-V processors. eFabless has created a chip harness pad ring, also one for sort of analog, meaning it's got some pass-through IOs and stuff like this, and it's kind of insert your IP here, and it's pretty cool. And some, if you, under certain conditions, with Google, like basically you have to publish your design, make it open source. They'll run your silicon for free. So there is some sort of a selection process. I'm not aware of the details, but you can learn about it from those slides in that talk.
Interesting. Well, thank you very much.
You're welcome. All right. I think that's it for questions. All right. Well, thank you all for the really good questions, and I'm so happy that we've got some folks who are just venturing into this field, it's my intent to senior folks can point out pitfalls, so I hope I've helped that way. And I mean no disrespect for folks who may not agree with the some of my stated misconceptions, but I'm not alone on those. And I know you read the textbooks, and it's like, why is this in there like that? And they're not wrong, okay, but they're just biased in a way that makes my field of microwave solid-state circuit design a little bit less accessible, and that's what bothers me, because it's not that hard if you conceptualize things. So onward and upward. What can we do for low cost? There's a lot to do, guys.
That's good talk, Tom. Thank you very much. And let me go ahead and introduce next month's talk. So for next month, the topic going to be terahertz communication at 300 gigahertz devices, packages, and systems. And the talk going to be provided by Dr. Ho Jin Song. He has a PhD in electrical engineering, and he's currently with the Department of Electrical Engineering at Pohang University of Science and Technology in Korea. He is a senior IEEE members and an IEEE Distinguished Microwave Lecturer for the 2019-21 term. In the talk, he will be presenting recent progress in semiconductor devices that make it possible to produce more power and lower noise at terahertz frequencies. The topic that will be covered includes discussions on terahertz radio front-end blocks, low noise amplifiers, modulators and demodulators, oscillators. And in the talk, the first prototype of terahertz wireless system will be presented. He will then overview technologies for implementing terahertz components and their performance. So please join us next month for this interesting talk. We'll be sending out invites if you're on our list. If not, please feel free to check in now on with us. Again, thank you very much and have a good night.